Mars is a small world. It is about half the size of Earth. Today, it is a place of extremes: cold, dry, seemingly silent. Its atmosphere is incredibly thin, a ghost that traps little heat and offers little protection. Rocks and ancient craters tell a story of lost vitality over eons. Any transient water quickly boils away or freezes. No flowing rivers, no vast lakes, no deep oceans. Mars waits, but imagine a different Mars. Air to breathe, warmth to keep, and the promise of life. The first change: increase atmospheric pressure. Today, Martian air is over 100 times thinner than Earth's. Without a pressure suit, a person would not survive. Thickening the atmosphere is the monumental first step. Higher pressure helps keep water stable on the surface. It also creates a partial shield, reducing radiation from the sun and deep space. But pressure alone is not enough. The air must contain oxygen. Mars air is mostly carbon dioxide, harmful for humans at high levels. Biology can help: engineered plants and microbes performing photosynthesis. They take in CO2 and release oxygen, as on Earth. Machines could accelerate the process, splitting CO2 into carbon and oxygen. Carbon becomes material. Oxygen enriches the sky. Next, raise the temperature with a denser, heat-trapping atmosphere. CO2 and water vapor absorb infrared radiation, preventing heat from escaping into space. Average temperatures rise, nights grow less severe, and seasons moderate. Warming can be seeded by sublimating polar dry ice, releasing CO2 already on Mars. Giant mirrors or albedo changes could jumpstart this greenhouse feedback. As temperatures climb, water vapor enters the air, amplifying warming. Permafrost thaws, trapped gases outgas, and Mars moves toward a temperate state. Warmth unlocks the next milestone: the return of liquid water. Liquid water is the cornerstone of life. With thicker, warmer air, water could persist in stable liquid form. Melting begins at the poles, seasonal streams becoming enduring rivers. Water follows ancient paths, carving new canyons and deltas. The low-lying northern hemisphere, Borealis Basin, could fill to form a new ocean. Over centuries, rivers pour into the basin as other depressions, like Hellas and Arger, become inland seas. Oceans stabilize climate, absorbing heat by day and releasing it by night. Water, universal solvent, enables the chemistry life needs. With oceans present, the stage is set for weather. Thicker air and open water ignite a global water cycle. Sunlight drives evaporation. Moist air rises and cools. Vapor condenses into clouds that ride new wind patterns. The Martian sky transforms: bright clouds, moving shadows, and rain-bearing fronts. Warm belts see rain. Polar and high terrain receive seasonal snow. Storms form, likely smaller than Earth's, but carrying wind, rain, and lightning. Deserts in rain shadows, humid coasts, icy poles, diverse climates emerge. Rain cleans dust from the air, paving the way for life to take hold. With stable air, warmth, water, and weather, life becomes the central question. Hardy microbes could flourish in soils, waters, and sheltered subsurface pockets. Engineered lichens and mosses pioneer, creating the first true soil. Grasses and shrubs anchor terrain and expand photosynthesis. Plants enrich oxygen and draw down carbon dioxide at scale. Algae, pollinators, and soil engineers form early food webs, carefully introduced. Agriculture expands from domes to open fields as conditions stabilize. Settlements move from underground to the open sky. A second home for humanity begins to feel real. Challenges remain: radiation and low gravity. A thicker atmosphere helps, but does not fully shield solar storms and cosmic rays. Colonists may retreat to well-protected, even underground spaces during events. At 0.38 g, bones lose density and muscles, including the heart, can weaken. Exercise, centrifuges, and resistance suits may mitigate health risks. Effects on plants, animals, and children born on Mars remain uncertain. Designing a balanced ecosystem is the most complex challenge of all. Missteps, invaders, or missing nutrient links could trigger collapse. For centuries, Mars would demand vigilant stewardship. Colonization would unfold in stages, starting long before full habitability. Small research bases build and test terraforming technologies. The effort demands colossal energy, new science, and cooperation across generations. Breakthroughs for Mars improve life on Earth, climate resilience, recycling, and biosphere design. A living Mars reflects our drive to explore, to understand, and to create. Scientific innovation can unify us and expand our view of life beyond Earth. What kind of world do we want to build on Mars, and why?